Wave theory, uniform plane waves, first one of the two parts, series on electromagnetic field theory, lecture number 4.20. Several types of electromagnetic waves are there. For example, uniform plane waves, cylindrical waves, spherical waves, TE waves, TM waves, so on, so forth. Out of all these, uniform plane waves, they are found to have certain special significance. The reason for their special status is in all wireless communication systems at the receiving antenna, when receiving antenna is separated from transmitting antenna by large distances, you can find this type of wave, that is uniform plane wave. Therefore, one can understand in wireless communication links where separation distance is 50 kilometers, 60 kilometers. This is for terrestrial links. If you consider satellite link, the distance is thousands of kilometers between transmitting antenna and receiving antenna. So in all these cases, the wave at the receiving antenna is uniform plane wave. This aspect speaks about the importance of uniform plane wave. Now, in the present session, we move further to explore the uniform plane waves. Before going to uniform plane wave, let us see what is a wave. If a phenomenon that occurs at one place at a given time is reproduced at other places at later times, the time delay being proportional to the space separation from the first location, then that group of phenomena is called a wave. If we go through this definition keenly, we can find that wave usually involves time repetition as well as space recurrence or spatial recurrence. These two, spatial recurrence, time repetition, these are important features of wave motion. However, a wave need not necessarily a repetitive phenomena in time as in case of tidal waves. There are certain exceptions. He is mentioning one exemption. It is uniform plane waves or UPWS in short, which are encountered frequently in practice, especially as I already mentioned, at any receiving antenna located at large distances from a transmitting antenna. It is a combination of three words: uniform plane wave. Wave, this term is already defined. Now we focus on the terms plane waves. Plane wave indicates equiphase surfaces or planes, and the word uniform refers to constancy of fields over equiphase planes. Electromagnetic uniform plane wave. What is electromagnetic uniform plane wave? Electric vector is there in this wave. Magnetic vector is there in this wave. That's why it is electromagnetic wave. So electromagnetic uniform plane wave is one in which electric, magnetic field vectors and propagation direction. These three are vectors. They are mutually orthogonal and they form a right-handed vector system with the fields being constant both in magnitude and phase over normal planes. So this particular para gives complete information, very good information, prime information regarding uniform plane wave. It says in uniform plane wave, electric vector, magnetic vector, direction of propagation, they are mutually perpendicular and also they form a right-handed vector system. In addition to that, the fields are constant in phase as well as in amplitude over planes which are normal to direction of propagation. From the definition, field requires to be constant in amplitude and phase over normal infinite planes. Infinite planes. What does it mean? Let us suppose wave is traveling like this. Wave travel direction is usually indicated by beta cap. The electric field, magnetic field requires to be constant over planes which are normal. Let us say we consider a normal plane like this. Normal plane, normal to direction of propagation. And field over this plane, electric field as well as magnetic field, their amplitudes as well as phases, they require to be constant when this plane is infinity in both the directions. So creating a field that remains constant from minus infinity to plus infinity is impossible. That's why he's telling plane waves cannot be generated. However, in many practical situations like signals reaching the domestic TV set after traveling large distances from TV transmitter, signals reaching the earth station after traveling great distances from the satellite in the skies, acquire almost plane wave fronts and hence can be approximated to a plane wave. Here is shown a typical uniform plane wave. To understand the structure of this uniform plane wave, we have to consider three aspects of uniform plane waves. What are they? First one, E, H, direction of propagation. They are direction of propagation, as I already mentioned, it is indicated by B cap. E, H, and B. These three vectors required to be mutually perpendicular. First one. Second aspect. These three form right-handed vector system. It means E cross H gives you beta, H cross beta gives you E, beta cross E gives you H. Second. Third one. Here this is a harmonic wave. Here variations are assumed to be sinusoidal. Time variations are assumed to be sinusoidal. Therefore, spatial variations are also sinusoidal. So harmonic wave. Keeping these three things in mind, when these things are in your mind, understanding this becomes quite easy. Let us consider the first one. E and H beta requires to be mutually perpendicular. Here direction of wave is along Z direction. E is X direction. H is in Y direction. Therefore, E, H direction of propagation. These are mutually perpendicular. So first condition is satisfied. Second condition, right-handed vector system. E is in X direction, H is in Y direction, E cross H is Z direction. So E cross H is giving direction of propagation. Similarly, H cross beta, we consider H cross beta. H is in Y direction, beta is in Z direction. So H cross B gives you, Y cross Z gives you X direction, E. So second thing is also satisfying. Third thing, variation is sinusoidal. Sinusoidal means you see here how it is varying. It is varying spatially in a sinusoidal manner. Okay. So once you have this idea, these 3 points in mind, understanding this fellow is quite easy. Even sketching also quite easy. You can consider wave journey in any direction you want, but with the help of these 3 points, you can sketch the wave, uniform plane wave. Here, the earlier slide is regarding graphical representation, which is of course helpful for visualizing the wave phenomena. Now here in this slide, we try to give expressions for electric field and magnetic field pertaining to uniform plane waves. Let us consider a harmonic wave traveling in plus or minus Z direction. The electric fields in time domain and phasor domains respectively. This is time domain, this is phasor domain. Notice wave is traveling in Z direction, that's why Z is there. Wave is a dynamic phenomenon, that is why time is there. Of course, when you convert into phasor domain, T is absent. E of Z equal to E naught E power minus R plus alpha Z. Alpha is attenuation constant. Cos omega T minus R plus. Here plus R minus is there, here minus R plus. Minus R plus. Beta is phase shift constant. Also note that alpha plus J beta is gamma, propagation constant. This aspect also you have to keep in mind. So gamma appears in one way or other way in the expression for fields. Here E is a vector and can have all the 3 components. E naught is amplitude, a complex vector in a plane normal to propagation direction, because electric vector requires to be perpendicular to direction of propagation. So E naught requires to be perpendicular to direction of propagation. It is traveling in Z direction, so E naught requires to be in XY plane or parallel to XY plane. The magnetic field can be obtained by replacing E by H. Now H naught, like E naught, is a vector plane normal to propagation direction. When medium is pure dielectric with no conductivity, gamma has to be replaced by J omega. What he is trying to tell is, when in case of pure dielectric, what happens is alpha is 0. Alpha, sigma is 0. When sigma is 0, alpha also becomes 0. So gamma has to be replaced by J beta or alpha by 0. When wave travel is in plus or minus X, plus or minus Y direction, then what happens? This is for plus or minus Z direction, these expressions. When it is plus or minus X or plus or minus Y, only thing you have to do is replace Z by X or Y. That's all. If the wave journey is in an arbitrary direction, then Z has to be replaced by X cos A plus Y cos B plus Z cos A, where A, B, C are angles the direction of propagation makes with X, Y, Z axis, and these are called direction cosines. In uniform plane wave, there exists a relation between E and H, impedance relation. The ratio E to H is called intrinsic impedance. Sometimes it is called wave impedance, sometimes it's also called characteristic impedance. But intrinsic impedance is the normal one, widely used term. Units are ohms. For this, it is indicated by eta. Eta, one can find eta equal to j omega mu by sigma plus j omega epsilon. Okay. Here, this is eta. It is in terms of this omega, sigma, epsilon. These are constitutive parameters. This expression is in terms of constitutive parameters. Eta in constitutive parameters. Of course, it can be converted into loss tangent also. Loss tangent is sigma by j omega epsilon. This ratio is, we know pretty well, it is loss tangent. It is usually indicated by tan delta. So eta can also be expressed in terms of tan delta dissipative factor in this manner. Okay. Intrinsic impedance, a little more information regarding intrinsic impedance. This is general expression. In case of perfect dielectric, sigma is 0, therefore eta becomes root mu epsilon. In case of perfect conductor, sigma tends to infinity, eta becomes 0. In case of good conductors, it is root of omega mu by sigma angle is 0.785 radians. Note, it implies in a wave traveling in a perfect dielectric, E and H are in phase. And wave cannot exist in perfect conductor. See, from this, I can say wave cannot exist in perfect conductor. In good conductors, E and H have 40 degrees phase difference. 0.785 is radians. In degrees, it becomes 45. So, this statement, this second one, this is general. This says that in a perfect dielectric, E and H are in phase. In perfect conductors, wave cannot exist because eta is 0. Good conductors, they have a phase difference of 45 degrees. Now, here we consider expressions, general expressions for the fields. We have already considered field expressions. Now, we are considering general expressions. The basic difference between those expressions considered just now and the expressions which right now we are going to consider is these are general in the sense where they are with respect to Cartesian system. Here expressions are in terms of position vectors. It means they can be used with any coordinate system. Okay, that is one difference. The second difference is right now we had some information regarding the ratio of ratio of E to H, intrinsic impedance. That information also we incorporate in the relations for fields. After incorporating that aspect also, whatever we got, that is being shown here under general expressions. ERT, E field is E naught cos omega t minus b dot r by naught. This is time domain. When you convert it, it becomes phasor domain. Okay? This is electric field. Now magnetic field. What is magnetic field in time domain? It is 1 by eta b cross E. Sir, what is this 1 by eta b cross E? Listen carefully. Here two aspects which we just considered right now, they are incorporated. What are those two aspects? One thing is E by H equal to eta. This aspect is incorporated. Therefore, H equal to E by eta. H equal to E by eta. So that's why eta is there, denominator. This is one aspect. The second aspect is direction of H is beta cap cross eta cap gives you direction of H. Because they form right-handed system. E, H, beta form right-handed vector system. Therefore, beta cross beta cap E cap gives you direction of H vector. Using that, this particular expression has come into being. Incorporating these two aspects, now one can easily understand. Okay, this second one is phasor domain. Here H naught is E naught by eta, E naught dot beta, H naught dot beta, E naught dot H naught is 0 because they are perpendicular. E and H are perpendicular, H and direction of propagation perpendicular, E and direction of propagation perpendicular. Therefore, they become 0. Here beta is bx x cap, byy cap, bz z cap. It's a propagation vector or wave number vector. R is position vector and phi naught is initial phase at the origin. When the medium is conductive, both fields get attenuated exponentially and magnetic field gets additional phase due to complex eta. As I already mentioned, in uniform plane wave, electric vector, magnetic vector, direction of propagation, they remain perpendicular to each other. In addition to that, they also form right-handed vector system. This is a mathematical statement pertaining to that particular fact or statement. Here, electric field and magnetic field they are shown with sinusoidal time variations, sinusoidal spatial variations. What he is telling is electric field and magnetic field remain in time phase always. In time phase always. Here one point I want to tell you, this statement is valid only when the medium is a perfect dielectric. If the medium conductivity is 0. Otherwise, if it is conductive medium, then we have seen already it is 45 degrees. Phase difference of 45 degrees exists. That thing you have to keep in mind. So this statement has to be taken with some reservation. In a uniform plane wave, in general, we have seen while studying a Poynting vector, there exists power flow, there exists energy storage in dynamic fields. When the wave is uniform plane, what is the power flow? In general, expression for power flow is E cross H. E cross H. General expression. It is valid for any type of wave, any type of dynamic field or any type of wave. But the expression that is specific to uniform plane wave is this one. Amount of power flow is given by E square by 2 eta or eta H square by 2. Of course, this has come from E cross H. E cross H. E cross is general expression. E and H are related in uniform plane waves. Incorporating all those changes, you will be getting like this. Direction of power flow is along wave travel. It is also associated with energy storage, whose average density is given by this formula. W average is epsilon E square by 2 equal to mu H square by 2. Here E and H are phasors or amplitudes. Another aspect worth discussion here is skin depth. What is this skin depth? Listen carefully. Let us suppose a wave is traveling like this, and it is falling over a surface of a material. If this material is a perfect conductor, this wave cannot penetrate into the conductor, it simply gets reflected. Of course, obeying laws of Snell's laws of reflection. Okay. Now, in case of if this material is a perfect dielectric, then it enters, travels and moves further. Remaining gets reflected. So, when in case of perfect dielectric, transmission is there, reflection is also there. In case of perfect conductor, only reflection. In case of perfect dielectric, transmission as well as reflection. Okay. In case of perfect dielectric, what happens is the wave travels through the material without any attenuation. It just travels without any attenuation. Now we consider a practical situation. A practical situation is one which is a good conductor. Let us say good conductor. It is not a perfect conductor. A good conductor. In such case, what happens is wave falls. After falling, what happens? It travels like this. By the time it travels a small distance, it gets died down. It dies. It travels with attenuation. After traveling a small distance, it dies down. Why it dies down? Reason is while traveling, it undergoes certain amount of attenuation. This attenuation is caused by conductivity of the material. So conductivity of the material decides amount of the attenuation. So how much distance the wave travels, it requires to be known sometimes. Okay? So that information is provided by, or to have that information, one parameter is defined. It is skin depth or depth of penetration. Some important points regarding depth of penetration. It is also known as depth of penetration. It is indicated by delta. To define, consider a wave falling over a conductive medium. Skin depth is defined as the distance by which the wave travels in the medium before it gets attenuated to 37% of its original value. Suppose in the beginning it is 1 volt. While it is entering into the medium, it is 1 volt. Into the conductor, it is 1 volt. How much distance it travels by the time this 1 volt becomes 0.37 volts? That distance is skin depth. It is related to attenuation constant of the medium. The relation is inverse of attenuation constant is inverse. Here you can see. For good conductors, skin depth is delta is 1 by alpha. Of course, alpha is for good conductors. We know it is square root of omega mu sigma by 2. So inverse cheste it lost. Right. Here 2 pi f. Omega is 2 pi f. If you expand it, ultimately you will be getting like this. In case of silver, conductivity is this much mu equal to mu naught. Substituting, you will be getting like this. So now we can notice skin depth depends upon several factors. Most important ones are frequency and conductivity. You can see here. And frequency is there. Conductivity is also there. Penetration depth is inversely proportional to conductivity under square root. It decreases with increase in conductivity and also inversely proportional to omega under square root. It is 0 when frequency and or conductivity are infinity. It is infinity when frequency and conductivity are 0. Another parameter, important parameter to be noted is the surface impedance ZS. Surface impedance. It describes the current opposing nature of the medium surface. So what is this? You see, when wave falls like this over a conductor, ordinary conductor, a good conductor, what happens? What happens is actually it travels a little bit distance into it, and by the time it travels some distance, it gets attenuated. Its strength becomes so small that we can neglect it. How much distance it travels to indicate that distance, skin depth is defined. Now, when wave falls over the surface of a conductor, another thing also happens. What is that? Currents flow over the surface. Certain currents flow. How much current exists? This current is an important parameter. Reason is this: antennas. Wave comes from the transmitting antenna, comes and falls over the receiving antenna. When wave falls over the receiving antenna is ordinarily a conductor plate or a conductor rod, conductor surface. When it falls, what happens? Currents flow. These currents are then handed over to the receiver equipment, which amplifies and process these currents to extract the signal. So currents, when wave falls, currents flow. What is the current? How much current flows? To determine the currents or to indicate the currents, a parameter is defined. That parameter is your surface impedance. With this understanding, let us go. To define, consider a traveling wave falling over a conductive medium. The surface impedance can be defined as the ratio of tangential electric field strength E tan at the surface of the conductor to current density K. It is surface current density of the current that flows as a result of wave incidence. Zs is by definition tangential electric field strength by surface current density E tan by K. It is a complex quantity. Real part is called surface resistance. Imaginary part is called reactance, Rs, XS. Surface impedance is related to propagation constant. It is gamma. This is propagation constant by conductivity. For a good conductor, Rs XS is equal to omega mu by 2 sigma. Surface impedance is 0 when conductivity is infinity, and in case of perfect conductor, it is infinity when conductivity is 0 for perfect dielectrics. For a thick good conductor, this is the story. In case of silver, he says Rs equal to Xs equal to, we see by substituting mu value, sigma conductivity value, you can have this kind of relation. Now, it is again a continuation. What is this continuation? Power loss. As I already mentioned, when wave falls over the surface of a conductor, wave falls. Wave is falling. It is a traveling wave. Traveling wave carries always certain amount of power. That power you can calculate using your pointing vector. The point is, it is a traveling wave, so some certain amount of power is there. Okay. When it falls, what happens? Currents flow. Okay, that is one aspect. Another aspect is it travels certain amount of distance with attenuation. That is also fact. We discussed about these two aspects. Another aspect is when current is flowing, naturally certain amount of dissipation happens. I square R loss. Joule's law. According to Joule's law, certain amount of dissipation happens. This dissipation is it is considered under power loss. We study about them in this slide. When wave falls over a conductor, current flows leading to power dissipation, which can be found from pointing theorem. This is pointing theorem. See, it is carrying certain power. It is falling over it. What happens to that power? That power is falling here. It is getting dissipated. Either over the surface or somewhat inside. Power is constantly falling over the surface. Therefore, it must be dissipating. It gets heated. So, this power that is there in this particular wave, it can be found using this one. Here, ET, are field phasors parallel to surface. This is pointing theorem. Listen, important point here is wave is there. It is carrying certain power. It is falling. The power is falling, and here it is getting dissipated. How much power is dissipated? The idea is, if you calculate the power in the wave, that gives you power that is being dissipated here. The power that is in the wave is pointing theorem. It is a conductor. Therefore, we know pretty well E and H have certain phase difference between. In a conductor, that phase difference is 45 degrees. So this can be put in this form. Cos 45. Cos 45 is 1 by root 2. So 2 root 2 ET. We also know that E and H are related by intrinsic impedance. So E is eta H. H. Using that relation, this one you got. Or you can replace H by E by eta. Then you will get it. So here eta is incorporated in the relations. Okay. Now another set of relations are shown here. Here instead of eta, here we are using surface impedance ZS. Okay. When surface impedance is incorporated, E becomes ZS HT, resulting in this expression. Okay. Ultimately, you will be getting ZS times K square. What is this K square? Listen carefully. When wave falls over a conductor, currents flow. They are surface currents. They are surface currents. Current density is indicated by K. As far as surface currents are concerned, current density is K. Okay. These surface currents, they are magnitude wise, they are equal to magnetic field, total magnetic field. Why I am calling total magnetic field? Reason is when wave falls, what happens? When wave is falling like you can see here, wave is falling like this, it gets reflected. So what is magnetic field here? It consists of two components. One component of the incident wave, another component of the reflected wave. Both put together, if you add them, then what you have is total magnetic field. This current K is numerically equal to total magnetic field. So this HT is there, na? He's talking about HT. This HT can be replaced by surface current. When you replace, you will be getting like this. But ZS also, listen carefully, ZS also can be replaced by RS. ZS and RS are related. If you replace, you will be getting 1 by 2 root 2 ZS equal to RS. Ultimately, you are getting like this, RS K square omega meter square. This is all what I want or I can share with you as far as uniform plane waves are concerned in the present session. Goodbye.